Right, I think when we are here, so let's get started with today's class. So if we recollect, we were looking at steps involved in constructing the root locus, and we essentially studied the first three steps, right? So we broadly observed that the root locus is used to capture the the locus of the closed loop poles as we vary a system parameter, and we essentially looked at a standard form for the open loop transfer function, and as a parameter k is varied. The question becomes, like how do the closed loop poles vary in relationship with the um, open loop poles and open loop zeros. So in that regard, we consider the standard transfer function, open loop transfer function, k times s plus z1 all the way to s plus z divided by s plus v1 all the way to s plus vn, and 1 plus that is equal to 0, k being a positive parameter. That's the first case we have started off with. And we completed three steps, right? So the first step was to locate the open loop poles and open loop zeros in the S plane. The root locus will have n branches, and each branch will start from one open loop pole as k starts from 0, and m of those n branches will end at open loop zeros, and the remaining n minus m will go to asymptotes or will go to infinity along asymptotes, right, as k tends to infinity. Then we locate the root locus branches or paths which lie on the real axis. We do that by taking a test point and counting the number of real open loop poles and real open loop zeros that lie to the right of this test point. And if that number is odd, then that point lies on the root locus. As we observe, that odd number comes because of the angle condition, right? Which necessitates that the face be an odd multiple of 5, right? For a value of s to be a closed loop. And the third step was to determine the asymptotes of the root locus, which applies only when m is less than n. And then, like we saw that the angle made by the asymptotes in the positive real axis is plus or minus 180 degrees times 2k plus 1 divided by n minus m. And the point of intersection was sum of open loop poles minus sum of open loop zeros divided by n minus. Okay, so this is where we stopped, right? So now we briefly started with the fourth step. Like we briefly understood what is a breakaway point and a break-in point, but let's recap, right? So that like we go from there, right? So if we look at a breakaway or a break-in point, so we saw that we will have, where did I draw that figure? Yeah. So essentially, if we have two open loop poles on the real axis, like in this example, -4 and 0, one branch starts from -4 and goes towards the right. One branch starts from 0 and goes to the left. At some point, they need to intersect on the negative real axis, and from there, they branch out into the complex plane. Okay, that is a breakaway point. Similarly, if we look at this particular figure, if at all, like in this example, we don't have that, but if we had, let's say, two open loop zeros on the real axis and two branches are terminating at them, right, as indicated here, very likely that two branches may come from the complex plane, intersect at a point, and then break into the real axis. Okay, so those are what are called breakaway and break-in points. Now, what is a common feature about breakaway and a break-in point? Please note that these are points where two branches of the root locus intersect each other. That means at that value of k, there is going to be a repeated pole as far as the closed loop poles is concerned, right? Because each branch we know that is a trace of one closed loop pole, right? So when two branches of the root locus intersect, that means at that point there is a repeated closed loop pole. Okay, so we are going to use that characteristic to derive this step. Okay, so please remember that. Let's go and look at this. So in step 4, we start here. So this is our open loop transfer function k times s plus z1 plus s all the way till s plus zm divided by s plus p1 all the way till s plus pn. So we call the factor s plus z1 all the way till s plus zm as some a of s. S plus P1 all the way till S plus Pn as some B of S. Okay, so what we are doing is that like the open loop transfer function G of S, H of S, we are writing as K A of S divided by B of S, just for simplicity of notation. Okay, nothing more than that. Okay, so we have consequently we have the closed loop characteristic equation as 1 plus K times A of S divided by B of S equals 0. Now, before we come here, let's look at this particular example, right? So if we look at this particular example, right, and then like we essentially then apply the step to the root locus example that we are studying, things will become clear. So let's consider a polynomial s plus 1 whole square times s plus 2. So the roots of the polynomial are -1, -1, and -2. Okay. So now, in this case, which is the repeating root? The repeating root is
-1.
-1, right? So by definition, the root of a polynomial is the value of s at which the polynomial will become 0. So please note that, let's say we substitute -1 or -2, d of s is going to be 0. That's the definition of root of a polynomial. However, when there's a repeating root, let's say we take the derivative of the polynomial with respect to s. So we take the derivative of t of s with respect to s, we get 2 times s plus 1 times s plus 2. Okay, when we take the derivative of s plus 1 whole square. Then if you take the derivative of s plus 2, I just get 1. So I just settle with s plus 1 whole square. So we use the product rule for differentiation. Now something becomes interesting, right? Since -1 is a repeating root which repeats twice, the first derivative of d with respect to this polynomial with respect to s is also 0 at -1. However, when we substitute -2, the derivative is not 0. Okay, so this is a unique property which happens or which comes into play when there is a repeating root. Okay, so I hope this point is clear. So in other words, if a root of a polynomial repeats twice, not only is the polynomial 0 at that value of s, but the first derivative of the polynomial with respect to 0 is also s at that value of s. Okay, so you and I are going to leverage this concept, okay, to our advantage. So how are we going to do this? We are going to apply that to 1 plus a times a s by b by s. So what we do is that, like, when we take the derivative is 1, it's constant, right? So the derivative is 0. Then we are left with k times a of s by b of s. How do I take the derivative of a of s by b of s? We use the ratio polynomial, sorry, differentiated derivative of ratios, right? So what we do is that we write the denominator square, and then in the numerator, first we differentiate the numerator multiplied by the denominator factor minus the numerator multiplied by the denominator factor. Okay, so this is how we calculate the derivative of ratios of polynomials, right? Or functions, what we call as a p by q rule and so on, right? When we learn calculus. Okay, so so essentially this becomes equal to 0. Obviously, b of s is what to say, we can take it to the other side. K is not 0. So what you and I get is a prime s b of s minus a of s b prime s is equal to 0. So in other words, if we solve this particular equation, figure out values of s. They are the potential values of s where there may be repeating closed loop poles. Okay, so they may be potentially breakaway points or break-in points. But then the best way to check is we come back to the closed loop characteristic equation, which is 1 plus k times A of s by B of s equals 0. From here, we can see that k I can write it as minus B of s by A of s. How did I get it? I just took minus 1 to the other side and then cross multiplied, right? So I get this. So we substitute the solution into this, and only when k is greater than 0, because that is a premise under which we are constructing these steps, right? Only for those values of s where k is greater than 0 are actual breakaway or breaking points, okay? So some will write the same equation as b prime as A of s minus A prime as B of s, okay? So that's how we would have written in the notes and many textbooks, okay? So it's the same equation, right? So we have just taken the factors to the other side, okay? So I hope it's clear how we got this formula, okay? So now let's apply it to our example. So in our example, if we recall, the open loop transfer function was k divided by s times s plus 4, right? So what do you think is A of s? If you compare with this,
It is K, sir.
it is 1, right?
Okay. Sorry.
If you look at this canonical,
Sorry.
yeah, k times A of s is k, correct, right? But A of s then will become 1, okay? So yeah, so this is just another canonical form that we are using around here, okay? So A of s becomes 1. So what will be B of s?
S plus S plus 4. S into S plus 4.
So I'm just going to write it as s squared plus 4s, okay? Just expanding it, right? So yeah. So from here, what will be A prime of s?
It will be 0, sir.
0, right? Because there is no s term, okay? So what will be B prime of s?
2S plus 4.
So we can see that that's what we have written here. So consequently, this equation here will become 2s plus 4 times 1 minus 0 is equal to 0. So consequently, we will get s to be equal to minus 2. Okay, so this is the potential breakaway point. Okay, so once we get this solution, we add a subscript b just to show that this is a potential breakaway point. And then we go and calculate the value of k at this potential breakaway point. Okay, so so essentially we go ahead and calculate minus of s squared plus 4s, that is b of s. A of s is 1 at s equals minus 2 or sb equals minus 2. So if we substitute it and calculate it, we see that in the numerator, s squared plus 4s becomes minus 4, but then there is a minus outside. Okay, so minus of minus 4 becomes 4. So, and that is positive. So we are having SB equal to 2 minus 2 as a breakaway point. Okay, so that's what happens in this particular example. So, sorry, this is example of break-in point. So, sorry, not this. Okay, so in this particular example, what has happened is that like this is what happens, right? So essentially one branch starts from minus 4, another branch starts from 0. At minus 2, they break in, and then they go out, okay, they branch out. And the value of k at the breakaway point is 4. Okay, so I hope it's clear how we did this stuff. All right. Okay. So any questions on this fourth step, you know, how to calculate breakaway break-in points? Okay. So anyway, we'll be doing more examples. Okay, so as we do more examples, these things will become much clear. All right. Okay. So now comes the next step. Okay, the fifth step. Once again, root locus construction is very methodical. Okay, so what we need to do is that see, many of these steps, as I told, you know, like nowadays, you know, we are learning so that you and I get an intuition when we do control design, right? The actual root locus construction, you know, like if you use the R locus command in MATLAB and all, we will be able to generate within a matter of few seconds. Okay, so but still, it is important for us to know the concept. That's why we are learning it. Now, what is the fifth step? The fifth step, once again, we do not read what is there within the parenthesis at the top, you know, like in the italics font. We locate the angle of departure from an open loop complex pole, right? So how do we calculate it? The angle of departure from an open loop complex pole is 180 degrees minus sum of the angles made by the vectors from other open loop poles to this pole, plus sum of the angles made by the vectors from open loop zeros to this pole. Okay, so how did we get this formula? Once again, let's let's understand what happened here. Let's understand the intuition behind this. Please, point number one. Please note that step number 5 applies only if you have complex open loop poles and complex open loop zeros. Okay. So in the particular example that we are considering, so what is the particular example that we are doing to understand root locus? The open loop transfer function is k divided by s times s plus 4. Okay, and k being a positive number. Okay, so we can immediately observe that there are no complex open loop poles, no complex open loop zeros. So in such a case, if we encounter such a problem, we can just write that this step does not apply to this problem. Okay. But then we are learning the general concepts. Okay. So let's figure out why this is the case. All right. So let's say, for the sake of learning, we essentially consider a complex open loop pole, which is here. Okay. So obviously the conjugate is also an open loop pole. So when we have an open loop pole, as we know, one branch starts from an open loop pole, right? The question is, which direction does the branch start? That is what is called as angle of departure. Okay, so now I hope the meaning of the word angle of departure is clear. When we had the open loop pole on the real axis and which is not repeating, we already observed that it can go either to the right or to the left. That means angle of departure was only 0 degrees or 180 degrees. But then if we have a complex open loop pole, it can go in any direction, right? That is the purpose of this step, okay? To calculate the angle of departure for a complex open loop. How do we do that? Still, please note, the open loop transfer function has to satisfy the angle condition, right? For the particular value of S to be an closed loop pole. So what we do is that, let us say without laws of generality, there is an pole, open loop pole here, open loop pole here, and an open loop zero here. We draw vectors from other open loop poles to this particular pole. Okay, that means we draw one vector which makes an angle phi1. We draw another vector which makes an angle phi2. And then from this open loop zero, we draw another vector which makes an angle theta1. Okay, with the real axis. Now, all these angles should satisfy the angle condition in the direction in which the branch starts from the open loop, complex open loop pole, which is here, right? And that is the reason why the angle of departure comes out to be 180 degrees minus phi1 plus phi2 plus theta. So phi1 plus phi2 is the sum of the angles made by vectors drawn from other open loop poles to this complex open loop pole. And theta1 is the sum of the angle, the only one open loop zeros in this example, right? The angle made by the open loop zero or the vector drawn by the zero to this particular pole under consideration. Okay, so this step applies only when we have complex open loop poles. Okay? We calculate the angle of departure using this concept. Similarly, we calculate
Sir,
angle of arrival.
I'm
Yes,
sorry, sir.
please.
Just sir, what is theta one, sir? Can you repeat, please? Possible, sir, please.
Theta one. See, I'm just considering a generic example, Roshan, without laws of generality. I have arbitrarily chosen an open loop zero. Let me redraw this figure. So let us say I have this, right? So what I do is that to figure out the angle of departure from this pole, I draw vectors from other open loop poles. Let me call this angle as phi1, this angle as phi2. Okay. And then I draw vectors from open loop zeros to this pole. Let's call this angle as theta. Okay. So that's what. Okay. So phi means is a symbol I am using to denote angle made by vectors drawn from other open loop poles to this open loop pole. Theta denotes the angle made by the vectors drawn from open loop zeros to this pole. Okay, I hope that is clear. All right. The formula comes because of the angle condition. That's all there is. Is it clear? No, sir.
Right, sir. Clear, sir. Clear.
Yeah. Similarly, of course, as I told, in this particular example, this step does not apply because there are no complex open loop holes, no complex open loops. Now, if we have an an open loop 0 which is complex conjugate, then as we know, one branch is going to end at the open loop 0, right? So then the question is which direction it will come in, right? And that is why the corresponding calculation is what is called angle of arrival. So when we have a complex open loop 0, we call it as the angle of arrival calculation on this complex open loop 0. So that is exactly the complement of this. That is 180 degrees minus sum of the angles made by other open loop zeros or vectors drawn from other open loop zeros to this open loop 0, plus sum of the angles made by the vectors drawn from all open loop holes to this particular zero. Okay, so you can see the symmetry in the formula. Okay, or the what to say? Essentially, I would say, similarity, okay, in the formula used for calculating angle of departure from a complex open loop hole and angle of arrival at a complex open loop 0. All right. Okay. So I hope this step is clear. Okay. This is step number 5. All right. So when we do not have a complex open loop 0 or a complex open loop hole, step 5 does not apply. All right. So that is the bottom. So is step 5 clear to everyone? So once again, as we keep doing problems, it will become much easier, right? So see,
sir,
yeah.
can I stop
Sir,
to
Yeah, please go ahead.
Yeah, because if you want, you can ask first.
Okay, thank you. So, sir, for this, can you go back to that slide? Sir?
Okay. Yeah.
Yeah. So, in our first example, when we are having this from open loop 0 to open loop pole, theta 1 angle I'm talking about. So, typically for open loop for zeros, we have arrow arriving towards.
That is when you want to calculate which branch arrives at the 0. But here you are calculating how the branch goes away from the open loop pole, because okay. So anyway, since this question has come, let me go a little bit more into theory. Okay. So since you have this question has arisen, so let me write down the general example, okay, which I have plotted here, right? So I have three open loop holes. Is that correct? Because like one open loop 0, right? So let's call this minus Z1, minus P1, minus P2, minus P3. Okay, all right. Okay. So now, what is the angle condition? Because so it should be angle of K is 0. It should be angle of S plus Z1 minus angle of S plus P1, right? Sorry. 1 minute, like 10 plus angle of S plus P2 plus angle of S plus P3 should be equal to plus or minus 180 degrees times 2K plus 1. I hope this fine, Vikas, right? I hope till here we are okay, right? Okay. Now,
Yes,
you and I need to find the angle of departure. Okay, so let me zoom into P1. Let us say I take a test point ST, which is very, very close to minus P1. Okay, I draw a vector, right? So this is the angle of departure, theta D, from this P1. Okay, so this vector is going to be ST minus of minus P1, which is ST plus P1. Okay, so that is what you and I want, the angle of that. All right. So now let's go back to this expression. So I choose this test point ST